So let's have a look at evaluation of classification models. Now, as you already know, classification models, target variables will be a categorical variable. Now for simplicity, let's assume we are considering a dichotomous categorical variable, which means you'll have two classes in a categorical outcome variable. So let's say a value like yes or no or pass and fail. And these are two distinct values that are available as the possibility in the categorical variable. Now, considering categorical outcome variables, what are the different metrics that we can leverage to understand the performance of a classification model? Now, the first and foremost, most important tool framework that is leveraged in this scenario would be the confusion matrix. As you can see over here, top left corner, this is what we call the confusion matrix. It's a simple 2 by 2 matrix represented for a binary classification problem. Now, since we have only two classes, 0 and 1, we are using a 2 by 2 confusion matrix. As the number of classes increase, so would the size of the confusion matrix would change. Now, how do we interpret this? Confusion matrix is a division between the actual classes and the predicted classes. So when you're saying the rows over here would represent the actual values of 0 and 1, the columns over here would represent the predicted values of 0 and 1. So the first row or first column would be when it is actually a 0, how many zeros were predicted, and when it is actually a 0, how many ones were predicted. So this would be a correct one, but this would be an incorrect one. Similarly, when the actual value is 1, how many of them predicted as 1? And when actual value was 0, so actual value is 1, how many of them were incorrectly predicted as 0? So based on the definition of 0 and 1, you can convert them to true positives and true negatives, and false positives and false negatives. So let's say 0 is negative and 1 is positive. So when a 1 is actually predicted correctly, that's a true positive. When a 1 is incorrectly predicted as 0, that will be false positive. Similarly, 0 will be negative. So a correct version of 0 would be actual would be 0, predicted would be 0. That's true negative. And when actual is 0, predicted is 1, that will be false negative. Now, the definition of true positive and false positive will actually change based on how you define 0 and 1. In some cases, you might just invert the definition of 0 and 1, and so would true positives and false negatives would also change. Now, from this simple confusion matrix, there are several bunch of metrics that we can calculate to understand how is a model performing. Now, the most simplest and one of the first metrics to be calculated would be the overall accuracy. Now, the overall accuracy, as you would interpret, would be out of all the classes, out of all the predictions made, how many of them were actually correct predictions. So you predicted 100 different you predicted for 100 samples. Out of these 100 samples, you're saying only 85 of them were like correctly predicted. So your overall accuracy would be around 85%. How do you get these numbers? So you have true positives and true negatives. These values combined together represent the entire total number of correct predictions. And the sum of all other four members would be the denominator, which would be the entire universe. So accuracy or overall accuracy can be defined as true positives plus true negatives divided by sum of true positives plus false positives plus true negative plus false negative. Now, there are cases where when overall accuracy won't alone let you understand the overall picture. So consider a fraud model. So when you're talking about a fraud model detection algorithm, you would have a scenario where out of 100 transactions made, 95 of them would be a genuine transaction and the remaining 5 would be a fraud transaction. So let's say you build a model which is useless. You predict all of them as a genuine transaction. So in a nutshell, what happens is you've predicted all of them as a genuine transaction. So 95 of them, which are actually genuine, you've correctly predicted them as genuine. But the 5, which were a fraud transaction, you've again incorrectly predicted them as a genuine transaction. But now the catch is, if you look at the overall accuracy, that would be 95 by 100. You've predicted correctly 95% of the use cases, or all the transactions. Now, the value 95 is really high, but then the remaining 5%, which is of really high importance, because that's where the entire importance of business use case will come in. Now, fraud transactions has collateral damaging effects. So let's say if you don't predict a fraud transaction as a fraud transaction, the kind of dangers that it will transfer to the business outcome is extremely high. So these are scenarios where you need to understand individually how is each class performing. So if we get one step deeper, we have precision and recall as one of the most important metrics used in this scenario. Precision would be true positive divided by true positive plus false positive. So if you just look at this matrix over here, we can say precision would be true positives upon true positive plus false positive. It means it's a fraction of correctly predicted values in the entire universe of one. And if you look at recall, that would be true positive upon true positive plus false negative. That's true positive upon true positive plus false negative, which means out of all the ones predicted, how many of them are actually correct. So both of them together combine and give you really powerful insights. And we have one more metric, F1 score, which is actually a combination of precision and recall together, combined under one roof, F1 score. Now, depending on the use case, and there are definitely a couple of others also. You have true negative rate, you have false positive rate. These are just easy to understand looking at the matrix itself. Now once you have the confusion matrix, you can easily calculate all of these metrics from the confusion matrix. Apart from the confusion matrix and its derived fixed metrics, we have ROC curve and the area under curve. Now the ROC curve is a plot where we can understand how is the model performing at different cutoff levels. It's a distribution of results between false positive rate on the x-axis and true positive rate on the y-axis. Now, if you look at this is the output ROC curve for a sample use case. Now, the way you would interpret this would be the higher area comes under this curve, the better your model is. So let's say this is the first curve. The second curve would be something like this. It passes from here. So there's a significantly higher amount of area under the curve. So that would be termed as a better model. Now the best model would be something which goes from here, touches all these edges, and then touches all these edges and right up to this point. That's like ideal model, which would be like having the highest area under the curve. So ROC curve coupled with area under the curve help us understand how is the model performing. Now, the blue line that you see over here is the baseline, which is 50% accuracy. Now, you're trying to look at how much lift do you have from the baseline. That's how you actually go ahead and interpret the ROC curve. So that was a brief on the different metrics that we would use to evaluate a classification model. Let's go ahead and look how we can codify these different metrics using a Python example.